It's one of the costliest engineering projects ever attempted, costing $1 billion. However, for it to realize its full potential, which is nothing less than rewriting the history of the universe and reshaping humanity's place within it, many factors must come together perfectly. Today, I'm going to talk about the James Webb Space Telescope, which is intended to provide answers to many of the fundamental questions that have occupied astronomers for the better part of the last half-century. It explains how, out of the tangle of molecules, stars, galaxies, black holes, and planets that make up the universe, the components essential for life arose and came together to form this place we call Earth. Is it possible that the circumstances that supported this flourishing environment could have occurred by chance? The vibrant surroundings that surround the JWST facility serve as a constant reminder of the Space Telescope's goal: to assist scientists in their efforts to comprehend how we got to where we are today. When it looks up, it will see terrifying lava planets complete with molten surfaces that whip around the sun in minutes. It will analyze planets that have somehow managed to escape the disastrous death of their stars and are presently orbiting the stellar corpses left behind. It will examine the atmospheres of gas giant planets, look for newborn worlds among the dusty disks that attach to young stars, and stare at a handful of small rocky worlds that may or may not be habitable. When it looks down, JWST must first survive a terrifying journey into space, followed by a sequence of events that have astronomers all over the world excited about the solar system. Apart from exploring planets beyond our solar system, scientists are also interested in learning more about the planet that we call home. The fact that Earth has liquid water, oceans, and oxygen makes it stand out from the rest of the galaxy, though these characteristics seem to be pretty common across the galaxy. In particular, Webb's extraordinary enhancements in sensitivity and resolution will allow us to develop a more complete picture of the objects in our solar system. By combining data from a variety of wavelengths and sources, including Mars and the larger planets, Webb is complementary to NASA's existing solar system programs, which include stations on the ground, in orbit around Earth, in deep space, as well as the International Space Station. Webb's extraordinary enhancements in sensitivity and resolution will allow it to investigate Pluto and Eris, two of the solar system's dimmer planets, in addition to the asteroids, comets, and Kuiper belt objects that are among the solar system's more insignificant bodies. With Webb's views of the outer solar system, researchers will be able to combine them with Cassini-Saturn data to get a more accurate picture of the seasonal weather on our large gas planets. In the outer solar system, there are certain characteristics in the spectra of the planets that indicate the presence of trace organics. Using Webb, scientists will be able to better comprehend the trace organics present in Mars' atmosphere and conduct research that will assist in confirming the results of the Mars missions. Since then, scientists have found hundreds of exoplanets in every kind of star system possible, and they are continuing to focus their efforts on finding smaller and more Earth-like planets. Soon, one of the primary applications of the James Webb Space Telescope will be to examine the atmospheres of exoplanets to look for signs of life. The first solar system discovered outside of our own did not include a main sequence star like our own, but rather a pulsar, which is a fast-rotating star. The Webb telescope, on the other hand, is an infrared instrument. What part does this play in the investigation of exoplanets, and how does it contribute to the field? The James Webb Space Telescope will employ the transit method, which means that it will look for a dimming of the light from a star when the planet is passing in front of the star. This is one of the ways it will collect data. Astronomers refer to this as a transit, and the joint effort with ground-based telescopes will help in measuring the mass of the planets using the radial velocity technique, which involves measuring the stellar vibration caused by the gravitational grip of a planet. After that, Webb will use the space telescope to perform spectroscopy of the atmosphere of the planet, followed by another collaborative effort with ground-based telescopes. In addition, Webb will be outfitted with coronagraphs, which will enable direct photography of exoplanets that are located close enough to their host stars. The picture of the planet would be a point on the surface of an exoplanet rather than a stunning panorama, but scientists have learned a great deal about the planet by examining that point. This includes the hue of the planet, the shifts in seasonal vegetation, rotation, and weather patterns, among other aspects that occur between winter and summer. The answer is in learning the steps involved in performing the spectroscopy. Once more, spectroscopy is the study of measuring the intensity of light at various wavelengths, And it is as simple as the fact that this kind of data is represented graphically in the form of spectra. Spectra are vital in comprehending the constituents that make up the atmospheres of extrasolar planets. When a planet moves in front of a star, the light from the star is reflected back into space only through the atmosphere of the planet. If the planet has sodium in its atmosphere, the star will have an absorption line in its spectrum because different elements and molecules absorb light at different energies. When it comes to describing the atmospheres of these exoplanets, scientists are able to predict where in a spectrum they may find the signature of sodium, methane, or water, if any of these elements or molecules are present in the atmosphere. Why is it necessary to have an infrared telescope? It is at infrared wavelengths that molecules in the atmospheres of exoplanets have the highest number of spectral features, hence making infrared observations useful. This is why doing infrared observations is advantageous. The end goal is to locate one of the countless planets in the Milky Way with an atmosphere that is analogous to that of Earth. As has been the case with many of humanity's most ambitious research and engineering undertakings, the journey to the launch pad for the James Webb Space Telescope has been plagued by technical delays and rising expenses. However, if everything goes according to plan, this flagship telescope, which is considered to be the successor to the iconic Hubble Space Telescope, should be a delicious feast of scientific discoveries. The name of the telescope has been the subject of dispute in recent years. Its extraordinary sensitivity will enable the observatory's gigantic golden eye to detect the faint, remote signals left by the earliest stars and galaxies that filled the galaxy once it is fully operational. Because of its sensitivity, the telescope will also be able to directly see alien life planets, even though no one could have anticipated using the telescope for this purpose. The infrared space telescope will observe the world primarily in infrared light. No one could have anticipated using the telescope for this purpose. It wasn't until 1992 that the very first exoplanets were detected, back when the observatory was first established. I don't think anyone ever brought up the prospect of there being other planets in the universe. The discovery of exoplanets did not occur until much later, when we first became aware that there were, in fact, exoplanets. The James Webb Space Telescope, JWST, is designed to revolutionize our understanding of the universe. While its primary mission is to study deep space, its potential extends beyond simply exploring the distant cosmos. Webb's infrared capabilities are expected to provide insights into the very earliest moments of the universe, long before our planet or even our sun existed. The first galaxies, which formed after the Big Bang, have remained shrouded in mystery for billions of years. Using JWST's unprecedented sensitivity, astronomers will be able to peer back in time to observe the formation of these galaxies, stars, and planetary systems. One of the JWST's most groundbreaking capabilities is its ability to study the formation of galaxies and the evolution of the early universe. By observing the universe in infrared light, JWST can look through cosmic dust clouds that often obscure objects in visible light. This is crucial for understanding the processes behind the birth of stars and galaxies, as well as for investigating the evolution of supermassive black holes, which are thought to exist at the centers of most large galaxies, including our own Milky Way. The telescope's ability to study these black holes, their accretion disks, and the gas surrounding them will provide insights into the extreme conditions in the universe's earliest stages. Moreover, the telescope's ability to detect the faintest infrared signals makes it particularly useful for identifying the earliest galaxies and stars. These signals will be key to understanding the cosmic dawn, the time when the first light in the universe emerged, nearly 13.5 billion years ago. JWST will capture the light emitted from these first stars, providing valuable information about the conditions that existed in the early universe and how the first elements, such as hydrogen and helium, evolved into more complex atoms and molecules. This is critical for answering questions about the origins of the elements that make up our universe today. The JWST's mirror, a giant 6.5-meter segmented primary mirror, is one of the largest and most advanced optical systems ever created. This large mirror is essential for gathering the faint light emitted from distant objects, such as the first galaxies, and focusing it onto the telescope's instruments. Each of the 18 hexagonal mirror segments is made of lightweight but durable materials, coated in gold to maximize the efficiency of infrared light collection. This intricate design allows JWST to achieve far higher resolution and sensitivity than previous space telescopes. In addition to its optical design, the JWST is equipped with 4 main instruments, each with specific tasks to study the universe. These instruments include the Near-Infrared Camera, NIR-CAM, the Near-Infrared Spectrograph, NIR-SPEC, the Mid-Infrared Instrument, MIRI, and the Fine Guidance Sensor/Near-Infrared Imager and Slitless Spectrograph, FGS/NIRIS. Each of these instruments will work together to capture a wide range of data, from high-resolution images of distant galaxies to detailed spectroscopic analysis of exoplanet atmospheres. The MIRI instrument, for example, will be crucial for studying colder objects in the universe, such as newly formed stars, faint galaxies, and even asteroids in our own solar system. Because MIRI operates at extremely low temperatures, it will be cooled by a special cryocooler system to maintain its sensitivity in the mid-infrared wavelengths. This will allow scientists to study the most distant objects ever observed, many of which are far too faint or distant to be detected by other telescopes. In addition to its scientific contributions, the James Webb Space Telescope is also a symbol of international cooperation. The project was led by NASA, with contributions from the European Space Agency, ESA, and the Canadian Space Agency, CSA. This collaboration has brought together the expertise and resources of multiple nations, each contributing critical technologies and instruments to the mission. The telescope's development, launch, and operation have been a testament to the power of global partnerships in advancing our understanding of the universe. The launch of JWST, set for late 2021, though this has been delayed, marks the culmination of decades of work. The telescope's journey into space is equally ambitious, as it will travel to a point beyond Earth's orbit known as the Second Lagrange Point, or L2. Located about 1.5 million kilometers from Earth, L2 is a stable point where the gravitational forces of the Earth and the Sun balance each other out. This location provides a clear, unobstructed view of the sky, while also offering a stable environment for the telescope to operate. Once it reaches L2, the telescope will undergo a carefully planned series of deployment steps. This will include the unfolding of its large sunshield, which will protect the telescope's instruments from the heat of the sun and maintain the extremely low temperatures required for infrared observations. The sunshield itself is about the size of a tennis court and will be made of 5 layers of a special material designed to block sunlight while allowing the telescope to remain at its operational temperature. Another unique feature of the JWST is its ability to study the solar system in unprecedented detail. By observing planets, moons, asteroids, and comets within our own solar system, the telescope will provide new insights into the formation and evolution of these objects. For instance, it will be able to examine the atmospheres of planets like Mars and Venus, looking for clues that could hint at past or present habitability. The telescope will also be capable of investigating the surface composition and weather patterns on distant moons, such as Europa or Titan, which are considered prime candidates in the search for extraterrestrial life. JWST's ability to study exoplanets in detail is another area where it will make significant contributions. By examining the atmospheres of planets outside our solar system, scientists hope to determine whether any of these worlds are capable of supporting life. The telescope's spectroscopic capabilities will allow it to detect trace gases like oxygen, methane, and carbon dioxide in the atmospheres of exoplanets. These gases are considered potential biomarkers for life, and their presence could be a strong indication that a planet is habitable. As we look toward the future, the James Webb Space Telescope is poised to become one of the most important scientific tools ever created. It promises to answer fundamental questions about the origins of the universe, the formation of galaxies and stars, and the potential for life on other planets. Through its observations, we will gain a deeper understanding of our place in the cosmos, and the mysteries of the universe that have eluded us for centuries will slowly begin to unravel. The discoveries made by Webb will not only advance our knowledge of the universe, but also inspire future generations of scientists and engineers to continue pushing the boundaries of space exploration. The James Webb Space Telescope, JWST, represents a leap forward in space exploration, not only in its technological design but also in its potential to answer some of the most profound questions about the universe. One key aspect of its mission is to help us understand dark matter and dark energy, two of the most elusive and mysterious components of the cosmos. These substances are thought to make up about 95% of the universe, yet their properties remain largely unknown. JWST's deep space observations will provide valuable data that could offer clues about the nature of dark matter and dark energy, potentially reshaping our understanding of physics. In addition to studying the distant universe, JWST will enhance our understanding of planetary systems within our own galaxy. By observing the formation of planetary systems, scientists hope to learn how other worlds develop and whether conditions suitable for life are common in the galaxy. Webb's ability to analyze exoplanet atmospheres will be especially important for identifying planets that might harbor life. Ultimately, the James Webb Space Telescope will not only serve as a scientific tool, but as a symbol of human ingenuity, collaboration, and curiosity. As we venture further into the cosmos, it will undoubtedly uncover discoveries that challenge our current knowledge and expand the boundaries of what we know about our place in the universe.